Okay, so all right. So again, we are using the same formula as we did for Euclidean term. Sine determinant P. Q coming here. D. D is equals to minus alpha beta 4 and BC. This in bracket AC B R plus here is now X, and here you have to ask X inside region R. Okay, so this is the formula for Tiemann's trick. So we have introduced last time. So we are going to use the same formula to replace this term, and multiply this sign. Okay, and then we are going to replace this A by hologram. Okay, and now the challenging part of the Lorentzian term is actually this K, this 2K. So we are going to find a way to express this K. And so you can see that this K is highly non-polynomial, because K, of course, depends on A. It depends linearly on A, but it depends non-linearly on E. Okay, so which means that K is actually a complicated expression. Well, it's actually at the very beginning, people see these formula for the Hamiltonian constraint. People just gave up at the very beginning because this K is too complicated. Yeah, it's hard to imagine how to quantize. But then later on, Thomas Tiemann comes, and he also invent what may be called second Tiemann's trick, or some other a few other Tiemann's trick. So Tiemann's trick is not the only one formula. This one is not only one formula like this, but it includes another trick for express this k in terms of Poisson bracket. Well, the trick by Thomas Tiemann is that we whenever we see some complicated expressions, things like this and k, we try to express them in terms of Poisson bracket, and then yeah, we can quantize Poisson bracket in terms of commutator. Okay. So now again, let me just introduce them with this. Well, I introduced by using a lemma. So first, you can express this Kaj. Yeah. So this is the quantity we want to simplify. So this can be written as a functional derivative of k bar, or some quantity k bar, Kj, respect to E. Yeah. And then these can be written as a Poisson bracket, because this is just a functional derivative with respect to fundamental variables, canonical variable. Can be written as a Poisson bracket between Aj, X, and this quantity k bar. Okay, so what is exactly this quantity k bar? This k bar is a three-dimensional integral over the entire spatial slice, and Kai, Eai. So this is just the trace of the extrinsic curvature. This is nothing but the trace of extrinsic curvature integrated over spatial slice. Okay. Right, and then you can see that we have expressed this Kaj in terms of a Poisson bracket between A and another quantity k bar. But then the question is how to quantize this k bar, how to express this k bar, because this k bar also still depends on k. Okay, so then another part of the trick by Thomas Tiemann is that you can express this k bar in terms of commutator. Right? This is 1 minus 1 over beta square. Again, beta is the image parameter. Poisson bracket. So it can be written as the integral x psi determine E and C0. So the Poisson bracket between a Hamiltonian Euclidean Hamiltonian constraint. So this is just the Euclidean Hamiltonian constraint integrated over the spatial slice and the volume of the entire spatial slice. Okay. Okay. So you see, this K bar can be written a Poisson bracket between Hamiltonian Euclidean Hamiltonian constraint and the entire volume, the total volume of the spatial slice. So you can see that the Euclidean Hamiltonian constraint, we are able to quantize, right? We have quantized that in the last lecture. And the total volume, we can also quantize. This is just the volume of the vertices by summing over all the vertices. Yeah. We can quantize that. Okay, so now we can express this K as a Poisson bracket of two quantities, and these two quantities can be quantized, right? And when we quantize this K bar, we can just replace this Poisson bracket by commutator, right? Once we have the quantum version of K bar, we can plug in this Poisson bracket, or I mean, at the quantum level, this should be a commutator again, and we can have the quantum version of K bar and plug in the commutator between polynomials, right, or between connections, and then we get a quantum version of a Kaj, right? So you can see that we have using these two tricks, we are able to express the extrinsic curvature in terms of some quantities we are able to quantize, but the price to pay is that we have to introduce several Poisson brackets. It's actually it's a double Poisson bracket. It's a Poisson bracket, but inside you have another Poisson bracket. Okay, so the calculation for the second part, so I'm going to skip because this is going to be complicated. It's not, yeah, it's to verify this expression, you have to really sit down and calculate. There's no way to compute it here. Too much time consuming. But I'm just going to give you a proof for one because this is really simple. The reason is that it comes from firstly Kaj. If you compute the functional derivative of Kvj x and delta Eaj y, it equals to 0. So if you plug in this formula, the expression for K bar inside, so you will okay, so you just need to compute the functional derivative with respect to E, but the functional derivative of Kai in terms of E is actually 0. Yeah, the reason is that because the Ashitaka variable, the canonical formalism in terms of Ashitaka variable, it comes from the canonical transformation of triad ADM variable. And in triad ADM variable, you have this Poisson bracket, right? Okay. So it means that K and E, they are actually independent variable. Yeah, and this Poisson bracket, the symplectic structure, or the structure of Poisson bracket is preserved when you go to the Ashitaka variable. So which means that if you compute Poisson bracket, even if you use Ashitaka variable, you compute the Poisson bracket between E and K, you should get the exactly same result. Yeah, it's just like, I mean, all the formulas are totally equivalent. Yeah? They are just the canonical transformation of one another, or you can view it's just a change of variables in your phase space. Right, so I mean, no matter what kind of variable you are using, ADM variable or Ashitaka variable or triad ADM variable, if you compute Poisson bracket of two different quantities, the result shouldn't depend on what variable you are using. Yeah? So which means that in Ashitaka variable, you should still get this expression. It means that K and E, they are actually independent variable. So which means if you compute the derivative of k in respect to E, you should just get 0. Yeah? So therefore, if you compute functional derivative of k bar with respect to E, it's nothing but you're just computing, well, the only thing contribute is the functional derivative of E with respect to E. Then you just get a delta function, you integrate delta function, you get kaj. Okay. So the first lemma is, the first formula in this lemma is very easy. Okay, but the non-trivial part is second one, but I'm not going to derive it for you, but I will encourage you to derive it by yourself. Okay. All right. So now let's accept these two formula, and then we are able to re-express the Euclidean, the Lorentz term of Hamiltonian constraint. Okay. So now we are able to write my determinant E CL equals kappa. So firstly, we plug in the expression for E, for a commutator of E. So we plug in this. Firstly, plug in this expression. So plus 1 is and you get some, get a epsilon a b c, and you get a factor of -4 theta. Okay, and these equals to combine prefactors 8 theta plus 1. Okay. Now you express this commutator. Well, I mean, you just use the expression of commutator kb minus kb ka r. Okay. And PC. Okay. Now you see that this AB, so this commutator is of course anti-symmetric with respect to AB, but this AB is contract with epsilon ABC, so which means that actually well, these two terms give the same contribution. So you just double the value of the prefactor. Okay, and then trace Ka, Kb, C, epsilon ABC. Okay, so it makes your expression shorter. And now you use the you use this expression for K. Okay. So you got 1664 4 3 trace AAQR B QR C B of R. Okay. Okay. So now you keep in mind that I'm not going to write explicitly this k bar in terms of this commutator because it will make the formula too long. But now you keep in mind that this k bar is expressed in terms of this commutator between Euclidean Hamiltonian constraint and total volume. All right. Okay. Now again, you can discretize this formula on the lattice, right? And you when you discretize this formula on the lattice, and you have to replace A's by holonomies, and and especially we have learned how to discretize this term, this factor, and remember we use that HEI inverse VV, and this V is for any, so this EI is odd for any edge toward the i's direction and located at adjacent to the vertex V, and this equals to minus xi, and here xi is the coordinate adapt to the lattice. Okay, of course, plus order, high order of coordinate lattice spacing. Okay, so it means that this formula holds only at the continuum limit. So that's why it is called a discretization of the Hamiltonian constraint. And similarly, you can imagine this A commutator with K can be expressed similarly. And you should have a discretized version of K bar equals to, so I will write a discrete version of K bar in a moment. It's just straightforward. Okay, and what is this K bar? K bar equals to minus 1 over beta square commutator sum over all the vertices and C0V, the discrete Hamiltonian constraint, discrete Euclidean Hamiltonian constraint, and also summing over all the vertices of the lattice and volume of the lattice, the total volume of the lattice. Well, so this is what we do for discretization. Okay, so these three formula is the quantity we use. It is the discretized version of those building blocks in the trace. Okay, and we are just to use them for the discretization, and all the other procedure are exactly the same as the Euclidean term, the discretization of the Euclidean Hamiltonian constraint. And so what you are going to do is just write this expression, integrate on one of the cubes, on one of the cubes, and then summing over all the 8 cubes around the vertex, and then making the average. So divided by 8. Okay. So when you divide by 8, you just replace the prefactor 64 by 8. You just divide by 8. Okay. Okay, and also you see that when you replace the commutator, the Poisson bracket by holonomies, okay, when you have the discretized version of those Poisson brackets, you have an overall minus sign. You have overall minus sign of this formula, and you have 3 factors, so which means you have overall minus sign, which cancel this overall minus sign. Okay, so which means the prefactor should be 8 plus 8 divided by kappa 4 beta c. Okay, so now we can just write down the discretized version of Lorentz term of Hamiltonian constraint located at a arbitrary vertex. So 8, 4, 3, and then plus 1. Then S. So similar to the Euclidean term, we have different orientations at different cube. So that's why you have to put a sign factor. Then I1, I2, I3. Okay, and trace. I1 S1. Inverse K bar. HEV S2. Sorry, here it's not yet commutator. So that's all the factor in the trace. Okay, so this is just a discretized version of C, and here it is expression for K bar. Okay, so you see we have expressed the Lorentz term in terms of elementary variables, holonomy, and flux. Of course, and you have to store some of the variables. So here holonomies are very explicit, and some of the variables are stored in the Euclidean Hamiltonian constraint inside Poisson bracket, and also the volume operator, the volume in the Poisson bracket. Okay. So, now the quantization is again straightforward. You can write the quantum Lorentz term. You just replace everything again by quantization. What you do is replace all the quantity by corresponding operators, and also Poisson bracket replace to 1 over I H bar commutator. Okay. All right. So now I think we are able to write down the quantum Hamiltonian constraint, quantum Lorentz term in Hamiltonian constraint H bar power 3, because you have 3 Poisson brackets. Kappa 4 plus 3 8 plus 1. Okay, and trace and holonomy operators, and now commutator. Now this K bar has to be operator as well. Okay. Well, what is this K bar operator? This K bar operator is just to replace the Poisson bracket by commutator divided by H bar. Commutator over V. This is just a Euclidean Hamiltonian constraint operator. Okay. And volume operator. I2 S2. Okay, so this is the operator version of the Lorentz term in Hamiltonian constraint. Okay, and the total Hamiltonian constraint is just summing these two terms, the Euclidean term plus the Lorentz term. V operator plus C of V. Okay. Now, so this quantity, you can see that it is not exactly the quantization of the original Hamiltonian constraint, but the difference is that we add a sign factor. So it's actually quantizing the Hamiltonian constraint multiply an overall sign factor. The reason is that we use the Tiemann trick for this term, for this EE term, and this EE term, and using the Tiemann trick, it gives a overall sign factor. Okay, so these actually quantize sign determinant E multiply C x. Okay, but since it is a constraint, you multiply a sign factor, it's still a constraint. Right? It doesn't break. So constraint equals to 0. You multiply a sign factor, it's still 0. Okay, and then these C hat operator, it acts on the Hilbert space of loop quantum gravity containing gauge invariant wave functions. So it means that this is gauge invariant. This is SU2 gauge invariant. So there was a homework asked you to prove that the Euclidean term is gauge invariant, and this is works exactly the same way. This is the Lorentz term is also gauge invariant. So it acts on gauge invariant wave functions, and the result is still gauge invariant. Okay, so this is the Lorentz term in the Hamiltonian constraint. And that time, when in 1996, 1997, when Thomas Tiemann first invented the quantization of the Lorentz term and the Euclidean term, at that time it was really a development. It's really an advance in quantum gravity, because in earlier quantization using ADM variable or traditional way of doing quantum gravity, the big problem, the biggest problem is the Willard-Witt equation. Yeah. And because Willard-Witt equation was a functional differential equation, is only can be written down formally. It's hard to define an operator on certain Hilbert space. But now, in 90s, Thomas Tiemann invented these operators, and it really make Hamiltonian constraint well defined, and at least make the constraint equation, make the Willard-Witt equation well defined as an operator equation. Okay, so that time is really a development of quantum gravity. Okay, so now we finish the quantization of Hamiltonian constraint on the lattice, and now we can talk about in the end the diffeomorphism constraint. And the treatment is very similar to the Hamiltonian constraint, or very much similar to the Euclidean part of the Hamiltonian constraint. Okay. Well, this is the diffeomorphism constraint. Equals 2 theta. F A B K and E B K. Okay, and it turns out that this expression, it cannot be quantized. But at least at the moment, nobody knows how to quantize this expression as an operator. Yeah, so one can. There was a traditional way to instead of quantizing this expression as operator, but quantizing finite diffeomorphisms and act on spin network states. Yeah? So you can, although you cannot quantize this expression, but what you can do is quantizing the finite diffeomorphism. You are not quantizing the generator of diffeomorphism, but you quantizing finite diffeomorphism acting on the spin network. Okay, that was a popular scheme for quantizing diffeomorphism constraint. But this is not something what we are going to talk about, because it turns out, well, it was useful as some perspectives, but for some very recent development, it wasn't so useful. Okay, so what is useful is still looking at quantizing generators. Okay, so looking for quantizing generators, but not exactly this expression, but we're quantizing a little bit modified expression we call EJ, and which is just well, conventionally we put a 2 in front, and you multiply EA by a triad. You contract this CA by a triad EAJ. Okay? So this EAJ is just a triad, just the basis. Okay, and you see, well, this is CA is a constraint, and you multiply the CA by a non-degenerate triad, yeah, it still preserves the constraint. So CJ is still a constraint. Constraint multiply, well, constraint making linear combination still give you constraint. Okay, so this CJ is completely equivalent to the diffeomorphism constraint, but this CJ is easier to quantize. So let me write down the expression. And the prefactor 2 is completely conventional. So it's useful for, well, it is conventional for some later on discussion. Maybe E A J E B K divided by determinant Q. Okay, so you can see that you so this EAJ combined with this E in this capital E in the diffeomorphism constraint, you get again a EE term, EAJ EBK divided by square root of Q, and this is a term you should be familiar with. We have discussed by using as one of the Tiemann strips. All right. So now you can see once you have the EE determined by divided by determinant Q, you are wondering maybe we can re-express, right? Re-express them as a commutator between E and E, and then re-express them as a Poisson bracket between connection and volume. Okay. So let's see what is going on here. So now let's consider this quantity, trace tau j FAB EA. Okay. You can see that, and this is just this quantity is just the Euclidean Hamiltonian constraint, but you insert in the trace another generator of SU2 tau j. Okay, j equals 1, 2, or 3. Okay, so here I'm going to derive is that this quantity, it is just FEE. Yeah, this is just this quantity. Yeah, so this quantity, of course, up to a prefactor. So this quantity will be equivalent to this modified diffeomorphism constraint. Yeah. Right. Okay. So these we can compute this this commutator. Okay. So this is trace, write everything in terms of components. Tau j So this is, yeah, we just express FAB. This is a matrix. This is FABI multiply tau I, sum over I. Okay, and similar for E. Yeah, and we know the commutator between two generators is given by epsilon KL M tau M half. So satisfying SU2 Lie algebra commutation relation. All right. So now we pull out all the numerical factors, all the factors which is not a matrix. K, L, and epsilon K, L, M. And now we're left with trace of 3 taus. Tau J, tau I, tau M. Okay. All right. And now we know that tau equals to minus I times the Pauli matrix. So this guy is just I times trace of 3 Pauli matrices. Sigma J, sigma I, sigma M. Okay, and we know that this trace of Pauli matrices is just give you epsilon symbol. So this I times 2I epsilon JIM. Okay, this is just identity for Pauli matrices. All right, so now we got contraction between 2 epsilon. So now we put everything together. This is minus 1/2 AB K BL and epsilon KL M and epsilon JI M. All right, and we use the identity for contracting epsilons. This is just 2 times delta K delta IL and KL anti-symmetrized. But this anti-symmetrization between KL is really free because firstly AB is anti-symmetrized, and so this AB is anti-symmetrized, and that's why KL is also anti-symmetrized. So we can freely remove this this square bracket, and just the result is just a minus. These 2 cancel with these 2, minus I B E A J E. Yeah. Okay. Well, you can compare. Well, let's try. Maybe I make it smaller so you can compare this formula and this formula. You can see they are really well. Of course, up to a 1/√, determine Q, and up to the prefactor. So you see, and these are just the same. Yeah. So therefore, we can express our diffeomorphism constraint in terms of something like this. And this is just, you see, this is very similar to the Euclidean term in the Hamiltonian constraint. The only difference is that we insert in the trace a Lie algebra generator. Okay, so all the treatment will be the same for the, will be very similar to the Euclidean term in Hamiltonian constraint. And now it applies to the diffeomorphism constraint. Okay, so now we can write the diffeomorphism constraint or modified diffeomorphism constraint to be minus 4 divided by kappa theta trace okay AB Q and commutator B. Okay. Now, and